So students, our today's topic is modification of the distribution law with change in molecular state. Now we know that according to distribution law, ratio C1 upon C2 is constant, or we can write K is equal to C1 upon C2. But this expression is valid only if the solute has same molecular state in both the solvents. However, if the solute undergoes association or dissociation in any one of the solvent or enters into chemical combination with any one of the solvent, then this expression does not remain valid and distribution law gets modified. So, depending on the interaction of the solute with the solvent, we can have different cases for distribution law and it gets modified accordingly. So different cases are: case 1, if solute undergoes association in one of the solvents. Case 2 is if solute undergoes dissociation in one of the solvent. Here association means that solute is combining with one of the solvent, and in second case dissociation means that solute is breaking into two parts in any of the solvents. And case 3 is if solute undergoes dissociation in both the solvents. It means solute is dissociating in solvent 1 as well as in solvent 2. And last case is if solute enters into chemical combination with one of the solvents. So first we shall discuss first case, which is if the solute undergoes association in one of the solvent. So what is the meaning of association? I told you earlier, means solute molecules are combining among themselves in one solvent. So for this, let us consider a solute X which is present in normal molecular state in phase 1, and in phase 2 small n number of molecules of X are undergoing association to form complex molecules Xn. This is shown in the diagram. You can see here I am having two phases, phase 1 and phase 2. Now I have dissolved X molecule in between the two solvents, and X is remaining in the normal state in phase 1 and its concentration is C1, marked in orange, and the concentration of the solute X in phase 2 is C2. Now as the solute can go from phase 1 to phase 2, so I can say that it will be in equilibrium in between two phases. Now in phase 2, if it is undergoing association, then I can write n molecules of capital X or solute molecules are forming X molecule, are forming a complex Xn. Here Xn means X represents solute molecules and N represents number of molecules of solute which are combining with each other. So we can say that solute has undergone association. Now in this case two equilibria can exist simultaneously. One is X in phase 1 in equilibrium with X in phase 2, mean solute present in same molecular state in phase 1 and phase 2. And second equilibrium that can exist is n molecules of X in equilibrium with complex Xn. Now let the total concentration of the solute X in phase 1 is equal to C1 as I told you earlier, and the concentration of solute in phase 2 is equal to C2. Now if I assume that alpha is the degree of association. What is degree of association? Means number of molecules or fraction of the molecules which are combining with each other. So if alpha is the degree of association of the solute in phase 2, then the concentration of associated molecules in phase 2 can be written as, here I have written X subscript n in square bracket. It means molar concentration of complex will be equal to 1 by n into C2. Is it clear? Therefore, the concentration of normal molecules in phase 2, I am saying that if the concentration of complex molecules is 1 by n C2 and degree of association is alpha, then if I have taken unity total concentration, then how many molecules will be left in the phase 2? I can say initially I have taken 1 and degree of association is alpha, then number of solute molecules left after association will be 1 minus alpha. So therefore the total concentration of normal molecules in phase 2 will be equal to C2 into 1 minus alpha. Is it clear? Now applying distribution law, now you have to keep in mind one thing, that distribution law is applicable to the same molecular state of the solute in both the phases or both the solvents. Therefore I can write concentration of X in phase 1 upon concentration of normal molecules of X in phase 2. Why I have written here concentration of normal molecules of X in phase 2? Because in phase 2 X is present in normal state as well as in combined state. So here I am saying that distribution law is applicable to same molecular state in both the phases. So I am considering normal molecules in phase 1 and phase 2. So I have written here expression in blue, concentration of, or blue ball pen, concentration of X in phase 1 upon concentration of normal molecules of X in phase 2 is equal to K, where K is partition coefficient. You already know it. Now I can write this equal to C1 upon C2 into 1 minus alpha, because you can see here the concentration of solute in phase 1 was C1. So I have replaced this by C1, and concentration of normal molecules of X in phase 2 is C2 into 1 minus alpha. So this will be equal to K. This is equation 1. Now applying law of chemical equilibrium to the second equilibria. Second equilibria is that for the association. So, or I can say for the process of polymerization. So applying law of chemical equilibrium to the second equilibria, that is for the process of polymerization, we can write equilibrium constant as concentration of associated molecules in phase 2 upon concentration of normal molecules in phase 2. So this will be raised to power n, and this will be equal to K into this will be equal to equilibrium constant, which I have expressed as K equilibrium. Now I can also write it as, because concentration of associated molecules in phase 2 that I showed you earlier is 1 by n into C2 alpha. So I can write 1 by n into C2 alpha upon C2 into 1 minus alpha raised to power n is equal to K equilibrium, that is equilibrium constant. Now taking nth root on both sides, we can write under root C2 alpha n or nth under root of C2 alpha upon C2 into 1 minus alpha is equal to constant. This is equation 2. Now dividing equation 1 by 2, we get, because if I divide 1 by 2, then C2 into 1 minus alpha in both the equations will cancel out. So I can write C1 upon nth under root of C2 alpha is equal to constant. This is equation 3. Now molecules in phase 2 are completely associated. Now if I assume that molecules in phase 2 are completely associated, then I can say that all the molecules are associated. It means alpha will be equal to 1. Therefore equation 3 becomes C1 upon nth under root of C2 is equal to constant. Why? Because alpha is equal to 1. So this is equation 4. And what is n? Here n represents the extent of association of molecules, mean how many number of molecules are combining 1, 2, 3. So this is the expression for distribution law if the solute undergoes association in one of the solvent. Here it represents, I have taken under root of C2. So it means that solute is undergoing association in second solvent. So this is the expression for distribution law if solute undergoes association in one of the solvent. And an example of this is benzoic acid. Now if I study the partition coefficient of benzoic acid between benzene and water, then it has been found that benzoic acid exists in the form of dimer. Dimer here means the two molecules exist, and I have shown this in the text. Dimer is represented by C6H5COH twice. But keep in mind that benzoic acid exists in this dimeric form only in benzene, but not in water. And in water it exists in normal state. Hence, the normal distribution law K equal to C1 upon C2 is not applicable. It means that if I will apply K equal to C1 upon C2 for this system of benzoic acid in benzene and water, then value of K by using C1 upon C2 will not come out to be constant, and a fairly constant value is obtained for or by using C1 upon relation C1 upon under root C2. This shows that benzoic acid exists as dimer in benzene. So this is the expression or all about modification of distribution law when solute undergoes association in one of the solvent. Now I am coming to the second case, case 2, if the solute undergoes dissociation in one of the solvents. So please see on this diagram, here I have represented or I have taken solute X which is in equilibrium with in both the phases. Now the solute, the concentration of solute in phase 1 and phase 2 is C1 and C2. But see here, in the phase 2, solute X is dissociating into molecules A and B. So if alpha is the degree of dissociation of solute in phase 2, then the concentration of dissociated molecules can be represented by C2 into 1 minus alpha. This is I have shown in orange circle. So if the solute undergoes dissociation in one of the solvent, then I can say let we are having a solute X which remains in normal molecular state in solvent 1 and undergoes dissociation in solvent 2, which I showed you in the diagram. Now two equilibria can exist in this system. One is equilibrium for undissociated solute X molecules in between two phases, and second one is the equilibrium between undissociated X molecules and dissociated molecules in phase 2, as shown in this screenshot. You can see at 1 I have written X in equilibrium with X. So here the solute X is in equilibrium with both the phases. So this equilibrium is for undissociated X molecules, and the second equilibrium is for the dissociated and undissociated molecules. Now if the total concentration of solute X in phase 1 is C1 and the total concentration of solute X in phase 2 is C2 and degree of dissociation of solute X in phase 2 is equal to alpha, then the concentration of undissociated molecules in phase 2 will be equal to C2 into 1 minus alpha. Why? Because if unity was the initial concentration and alpha is the degree of dissociation, then number of left molecules will be 1 minus alpha and the total concentration will be equal to C2 into 1 minus alpha. Now applying distribution law to the same molecular state of the solute in both solvents, we can write. अब आपको ये ध्यान रखना है कि जब डिस्ट्रीब्यूशन लॉ अप्लाई करेंगे तो आपने सेम मॉलिक्यूलर स्टेट पे अप्लाई करना है. अब आपके पास यहाँ पे C1 भी है कंसंट्रेशन फेज 1 में और C2 और सेकेंड फेज में कंसंट्रेशन है C2, पर मैंने कहा कि आपको सेम मॉलिक्यूलर स्टेट में अप्लाई करना है. तो सेम मॉलिक्यूलर स्टेट में जो फेज 1 में तो कंसंट्रेशन C1 है और फेज 2 में C2 तो टोटल कंसंट्रेशन है, पर सेम मॉलिक्यूलर स्टेट मतलब जैसी फेज 1 में थी मतलब अनडिसोशिएटेड, दैट इज इक्वल टू C2 into 1 minus alpha. So I can write C1 upon C2 into 1 minus alpha is equal to K. So this is the expression for distribution law if the solute undergoes dissociation in solvent 2. 2 here I mean, sorry, I have written it as TWO, but it is solvent number 2. Just a minute, I am correcting it, what I mean to say. Yes, now it's okay. Now on the other hand, if the solute undergoes dissociation 1, now I am saying if solute, in spite of undergoing dissociation in solute 2, it is undergoing in solvent 1, then the expression will just change a little bit, because solute is undergoing dissociation in solvent 1, so I will introduce the degree of dissociation term in first concentration term. So the expression will become C1 into 1 minus alpha upon C2 is equal to K, where alpha now represents the degree of dissociation of solute X in phase 1. So this is the expression for distribution law if solute undergoes dissociation in solvent 1. So I think now it is clear to you that how distribution law gets modified or distribution law equation gets modified. You have to just introduce the term alpha in the concentration term in which solute is undergoing dissociation. If it is undergoing dissociation in solvent 1, then you will insert alpha in the form of 1 minus alpha, and if it is undergoing dissociation in solvent 2, then you will insert it in C2 term, that is C2 into 1 minus alpha. Now I am coming to the third case. Case 3 is if solute undergoes dissociation in both of the solvents. Now if you understood the second case, now I am coming to the third case in which solute is undergoing dissociation in both the solvents. If solute is undergoing dissociation in both the solvents, then we will introduce the term alpha in both concentration terms C1 and C2. Okay, then if solute is undergoing dissociation in both the solvents, then the concentration of the solute in solvent 1 can be written as C1 into 1 minus alpha, and in solvent 2 will be C2 into 1 minus alpha. Therefore partition coefficient can be written as C1 into 1 minus alpha upon C2 into 1 minus alpha is equal to K. But now keep here one thing in mind, I have used alpha for both the solvent. It means the degree of dissociation is same for solute in both the solvents. This relationship or expression for distribution law is if the solute has same degree of dissociation in both the solvents. But it is not necessary that solute has same degree of dissociation in both the solvents. They may have different degree of dissociation. Now if the degree of dissociation of solute is different in both the solvents, then the above expression can be written as, see here with in ballpoint pen I have written C1 into 1 minus alpha 1 upon C2 into 1 minus alpha 1 is equal to K. So please note here that for degree of dissociation of solute in phase 1 I have written alpha 1, and so alpha 1 is the degree of dissociation of solute in phase 1, and degree of dissociation of solute in phase 2 is alpha 2. So expression for distribution law will be equal to C1 into 1 minus alpha 1 upon C2 into 1 minus alpha 2 is equal to K. So this is the expression for distribution law if solute undergoes dissociation in both the solvents. Now I am coming to the fourth case. Fourth case is if the solute enters into chemical combination with one of the solvents. Now what is the meaning of chemical combination? Please see here in this diagram I have taken X as solute in phase 1 in which no change is there in phase 1 and its concentration is C1. But when it enters into the phase 2, its concentration in phase 2 is C2, total concentration is C2. But in phase 2, solute X is combining with n number of solvent molecules whose concentration is CS, shown in orange circle. Now as solute X is combining with n number of solvent molecules and is forming a complex XNS whose concentration is CC. So this is the combination of the solute X with n number of solvent molecules. So now coming back, we are having a solute X which remains in the normal molecular state in solvent 1, and in solvent 2 one molecule of X combines with n molecules of solvent in phase 2 to form XNS. Is it clear? Then two equilibria can exist simultaneously in both the solvents. Now what are the two equilibria? First one is equilibrium for the distribution of solute molecule X in between phases 1 and 2, and second equilibrium is equilibrium between solute and solvent molecules on one hand in solvent 2 and the complex molecules on the other hand. Is it clear? So these are the two equilibria that I have shown by numbering Roman numbers 1 and 2. Now let the concentration of solute X in normal state in phase 1 is C1. As solute X is present in solvent 1 or phase 1 in normal state, so its concentration is C1, and the concentration of solute X in normal state in phase 2 is equal to C2. Now please note here that the solute is existing in two states in solvent 2. It is existing in normal state as well as in complex state with solvent molecules. So concentration of solute X in normal state in phase 2 is C2, and concentration of solvent molecules in phase 2 is equal to CS. Now the concentration of complex molecules in phase is equal to CC. Here this line is by mistake, so I am deleting it. It is repetition of second. It is by mistake. So now then applying distribution law to the same molecular state of solute in both phases, we can write C1 upon C2 is equal to K. This is equation 1. Here I was not having circle for showing equation 1, so I have represented it in red. So distribution law for this can be written as C1 upon C2 is equal to K. Now applying law of chemical equilibrium to the second equilibrium, we can write second equilibrium is this one, X plus NS in equilibrium with XNS, and their concentration is, now you have already studied law of chemical equilibrium, which states that the ratio of the molar concentration of the products, the ratio of the molar concentration of the reactants is constant, equal to equilibrium constant. So here on the product side it is concentration Cc, and on the reactant side it is C2 and Cs. So I can write law of chemical equilibrium will be equal to Cc upon C2 into Cs raised to power n equal to K1. This is equation 2, where K1 is equilibrium constant. Or by rearranging this equation, I can write Cc upon C2 equal to K1 into Cs raised to power n. I just rearranged this equation. Now for dilute solutions, the concentration of solvent in phase 2 is in excess. जब कोई डाइल्यूट सॉल्यूशन हमारे पास होता है तो हम उसमें मान के चलते हैं कि सॉल्वेंट बहुत ज़्यादा है सॉल्यूट के कंपैरिजन में. सो आई कैन से दैट फॉर डाइल्यूट सॉल्यूशंस द कंसंट्रेशन ऑफ सॉल्वेंट in phase 2 is in excess. Therefore its concentration Cs remains practically constant. Now if Cs is practically constant, then I can write Cc upon C2 is equal to K2, because here K1 into Cs raised to power n is constant, so I replaced that term with K2. So I can write Cc upon C2 is equal to K2 equal to constant. Now adding 1 on both sides of this equation, we can write 1 plus Cc upon C2 is equal to 1 plus K2, and taking LCM on left hand side, I can write C2 plus Cc upon C2 is equal to 1 plus K2. This is equation 3. Now dividing equation 1 by 3, 1 was C1 upon C2, so dividing equation 1 by 3, we get C1 upon C2 plus Ct plus Cc, because C1 by C2 in equation 1 will be cancelled out by the term C2 which is present in denominator in equation 3. So I will get C1 upon C2 plus Cc will be equal to K upon 1 plus K2 equal to K3, where C2 plus Cc is equal to total concentration of normal solute molecules and solvated solute molecules in phase 2. Therefore we can write total concentration of solute in phase 1 upon total concentration of solute in phase 2 is equal to constant. So what we can say? We can say that when solute molecules combine with solvent molecules, then the distribution law does not get modified. However, there is change in the numerical value of the constant. You can see that in place of K, we have written it in another term of another constant K3. So we can say that when there is combination with the solvent, then the distribution law does not get modified, but only there is change in the numerical value of the constant. So that was all about the different cases of modification of distribution law. Thank you.